Swayam Prabha. Digital India. Educated India.
This lecture is a continuation of the previous lecture, in which we were discussing estimation of binding constants in strong to ultra tight protein ligand interactions using differential scanning calorimetry. And since this lecture involves a lot of derivations, part of the derivations were covered in the previous lecture, and rest of the discussion we will continue in this lecture. So, just as a recap to what we did in the previous lecture was that we discussed that the optical methods or isothermal titration calorimetric methods are very good in a certain range for the determination of binding constants. And when it comes to determination of the binding constants of the order of 10 raised to the power 20, 10 raised to the power 30, 10 raised to the power 40 or even higher, then those methods cannot be applied. Differential scanning calorimetry offers a very good mode for the estimation of the binding constants in this high range associated with the binding of ligands with the biological macromolecules. With this background, we started discussing 1:1 binding mode interaction and developed certain equations. Now, let us take a look at the slides. So, what we discussed was that we should thermally unfold a protein and as well as thermally unfold protein ligand complex by the use of differential scanning calorimetry and obtain various thermodynamic parameters such as transition midpoint in the absence of ligand, transition temperature in the presence of ligand, total ligand and total protein concentrations that we already know, and we defined that delta Ht and Kt are the parameters for a reaction at temperature T, and prime we used for the unfolded state of the protein. And wherever we used equilibrium as a subscript, we said that it will be equilibrium constant for the unfolding process monitored by DSC at transition midpoint. Then we went ahead and used the Van 't Hoff equation. One can use any of these two forms to arrive at the final two equations which are mentioned in this slide. And these equations basically connect the K at a certain temperature with the knowledge of K at a reference temperature, or in other words K at temperature T2 with K at temperature T1 with the knowledge of the enthalpy change at that reference temperature and the corresponding heat capacity change, along with the temperatures T2 and temperatures T1. These we discussed in the previous lecture. Then we started with the binding stoichiometry for a single unfolding transitions and introduced these equations along with the expressions for their equilibrium constant and parameters set, and we arrived at these two equations for K equilibrium at a given temperature T and K equilibrium at Tm, which is equal to 1, and then finally we also came up with an equation which is for KLTM, and that KLTM, that is the binding constant that we are interested in, because KLTM can further be connected to KL at any temperature T. Now, let us discuss further. Since we know KT0 is equal to 1, why KT0 is equal to 1? Because T0 is the transition midpoint, and if the unfolding is two state, then the value of K at the transition midpoint is equal to 1, that we have discussed several times. Now, when we choose T0 as the reference temperature, please listen to this carefully. If we choose T0 as the reference temperature and substitute this KT0 equal to 1 in one of those two equations which we just discussed, the equations which connect KT2 with KT1. Now, here KT1 will be KT0 and that we will substitute equal to 1. So, what we will get? KLTM is equal to this expression. This is by using one of those two equations. Let me just go back and highlight that. By using one of these two equations and also by using this equation, what we arrive at is KLTM is equal to exponential of minus delta H naught at T0 by R into 1 by Tm minus 1 by T0. Tm is the transition midpoint in the presence of ligand, T0 is the transition midpoint in the absence of ligand, delta Cp0 is the change in heat capacity, and this concentration of L at Tm is the concentration of the ligand at the transition midpoint. Now, here we are talking about the binding which is very strong. The binding constants which are of the order of, let us say, 10 raised to the power 20 to 10 raised to the power 30 to 10 raised to the power 40. That means the binding is relatively strong. If the binding is strong, obviously the transition temperature of thermal unfolding in presence of ligand and associated bindings will also be high. So, what is observed, that if the binding is very, very strong, then let us take a look at this slide. This entire quantity within this bracket is much higher than 1. So, 1 can be easily ignored because exponential of this factor is going to be much higher than -1. So, therefore, if you ignore -1 for tight binding conditions, we end up with this relation. KLTM is equal to all these factors. Now, let us move ahead. Let us look at these conditions. According to these conditions, the concentration of ligand at transition temperature is total ligand concentration divided by 2 if the ligand concentration is less than the total protein concentration. How do we interpret that? Let us say we have, this is the thermal unfolding of the protein in the presence of ligand. Now, if total ligand concentration is less than total protein concentration, that means there is no more ligand freely available, because the binding is very tight, no more ligand freely available in solution. So, therefore, when we have at transition temperature, write K, K is concentration of denatured state divided by the concentration of native state, right. And therefore, if we write about the concentration of the ligated complex at denatured state and at the native state, obviously both the concentrations are going to be half and half. And that is why the comment made over here that total ligand concentration at transition temperature, at transition temperature is equal to the total ligand concentration in solution divided by 2. That is, we are talking about, let me go to this slide, we are talking about what is the concentration of ligand at this point. Obviously, because K is equal to 1, and therefore, the concentration of the ligand at Tm is also expected to be half of the total ligand concentration. Now, let us take a look at the next comment, that total ligand concentration at Tm is equal to Lt minus Pt divided by 2 if total ligand concentration is much higher than protein. Now, here the concentration of protein is much lower and it is fully complexed, and therefore, when you again allow the protein to unfold, again at transition temperature K is going to be equal to 1, and therefore, the concentration of the ligated form and denatured form and concentration of the ligated in the native form are going to be same. And since here the protein is in small amount, it is fully complex, the total ligand concentration is going to be total ligand concentration at transition point. Let us take a look in the slide, is going to be total ligand concentration in solution minus total protein concentration in solution divided by 2 if Lt is greater than or equal to Pt. I repeat, the ligand concentration at transition midpoint is Lt by 2, Lt is the total ligand concentration in solution. If Lt is less than or equal to Pt, and the concentration of ligand at Tm is going to be Lt minus Pt by 2 if the total ligand concentration in solution is greater than or equal to the total protein concentration in solution. Now, if the heat capacity of binding are known from mixing calorimetry, then KLT can be determined from KLTM. This is the comment. How it can be determined? Let us take a look at this. Again, I am using one of those two derived equation where the final temperature I am keeping as T and initial temperature I am keeping at Tm, and we are applying this for the ligand binding. So, KL at a temperature T is equal to KL at a temperature Tm into exponential minus delta H naught L at T1 by R into 1 over T minus 1 over Tm plus delta CPL in standard state divided by R into log T by Tm plus 1 minus T by Tm. Now, the question is, for this we need to know the enthalpy of binding and heat capacity of binding. And if these two quantities are known from mixing calorimetry, suppose if we do not have the instruments which give both the K and delta H very accurately, but we have an instrument like ITC can give you very correctly the value of enthalpy of ligand binding even if the binding is very strong. So, if we can determine delta HL from there, from mixing calorimetry, and delta Cp obviously can be obtained if you determine the temperature dependence of delta HL, then we can fix over here. But if suppose if mixing calorimetry is not available, we do not have an ITC and we have only a DSC, then how do we get? Let us take a look at the equation. If the mixing calorimetry is not available, then heat of binding may sometimes be determined from DSC, and how we get delta H, this is what we are interested in, delta, either we say EXP or we can write HL, no problem. This is equal to the written equation. How it is? Let me explain that. In one of the previous lectures, we discussed that if you thermally denature a protein, let us say the corresponding value of the delta H is delta H1, and if I take PL and we form it P prime plus L, then I say delta H2. And if I am interested in the enthalpy of this reaction, then this is simply delta H is equal to delta H1 minus delta H2. But here you remember that we have to multiply by the fraction of the protein which is in the denatured state or fraction of the protein which is ligated. If we are assuming that completely denatured, completely ligated, then we put 1 over here, otherwise it has to be accounted for. Now, for this I can write delta H at temperature whatever it is here. If I am saying in the absence of ligand, then it will be equal to delta H at another temperature, or let me put this as T1, that will be easier. If I put T1, this will be delta H at T0 plus delta Cp into T1 minus T0. So, at any temperature we can connect it the enthalpy with the reference temperature and delta Cp. Now, let us go back to the slide and take a look at. This is what is done in this part. Just take a look at delta H T0 plus delta Cp into Tm minus T0. This is delta H1. And for the ligand binding part, when we talk about the unfolding of the ligand bound protein, then the fraction of the protein which is ligated is Kl into concentration of L plus divided by 1 plus KL into concentration of L multiplied by the enthalpy of ligand binding. Let me go back to this slide. I was saying that we need to put fraction over here and fraction over here, and here we are assuming that the protein is completely unfolded, and here we need to put the protein, the unfolding of the protein, the fraction which is ligated. How do we get that? We have P plus L is forming PL, and KL is equal to concentration of PL divided by concentration of P into concentration of L. How do we calculate the fraction of the protein which is ligated? If I represent that as FPL, this will be PL divided by concentration of P plus concentration of PL, because this is the concentration of protein which is ligated, this is the total concentration of protein whether it is in free form or in the ligated form. So, this is equal to, for PL I can write from here, this is KL into P into L, this I am using PL from here, substituting over here, and down there I have P plus, again for PL I will choose to write from here KL into concentration of P into concentration of L. Now, I can get rid of concentration of P, which is a common factor over here. So, fraction of the ligated protein is equal to then KL into concentration of P over, let me rewrite again, P plus KL into P into L, let us remove P. So, it is KL into L over 1 plus KL into concentration of L. Now, let us go back to the slide, and this is what is substituted over here. We use this fraction into delta HL. So, therefore, what we have is the enthalpy of ligand binding at any at transition temperature can be obtained. Now, we have derived these various equations. Now, let us discuss some equations which are required for simulations, because the idea is to do simulations to fit the theoretical model to experimental data points, so that we can extract the values of binding constant. That is the main purpose. Now, let us go back to the slide. Total protein concentration in solution is equal to the concentration of protein in the native form, which is free, the concentration of protein in denatured form, and the concentration of protein which is in ligated form. Now, from the earlier derived equations, we can substitute for concentration of P prime, we can substitute for concentration of PL, and we will end up with this equation, which is concentration of P plus K times concentration of P plus KL into concentration of L into concentration of P. Similarly, the total ligand concentration is sum of the concentration of ligand in the free form plus the concentration of ligand in the complex form. And again for the concentration of PL, by using one of those equations earlier discussed, I can write in terms of concentration of L and concentration of P. Now, you see, if I know the total protein concentration and if I know the total ligand concentration, then I can get the concentration of L as well as the concentration of PL in the free form. Now, if you combine these two equations, it will take a quadratic form, the solution of which can be expressed as the concentration of L is equal to minus B plus minus roots B square minus 4AC divided by 2A. Minus will give an imaginary the number which is not acceptable, that is why plus is retained, and where A is KL, B is equal to 1 plus K plus KL into PT minus LT, and C is equal to minus LT plus K into 1 plus K. So, this sum maths has to be done. Therefore, after doing this, what we have, the input parameters from the DSC: transition temperature in the absence of ligand, delta H in the absence of ligand, delta Cp, KL T0, delta HL T0, delta CPL, PT and LT. The concentration of P is expressed in this form, and the concentration of PL is equal to KL into P into L, and KT is given by this equation. These equations we have earlier discussed, and going a step ahead by using one of those two equations which I discussed in the beginning, I can write KLT is equal to KL T0 into exponential all these terms, regarding which I have already discussed how to get this. Now, the question is, when you want to get KL, we need to know the concentration of P and the concentration of L in the free form, and we have just discussed how to get the concentration of P and concentration of L by using the equations under the simulations head. So, therefore, when you talk about the excess enthalpy relative to P0, we just discussed some time ago how to express the enthalpy: fraction of the protein which is in the denatured form into the corresponding delta H plus fraction of the protein which is in the ligated form into the corresponding delta H. And we have discussed how to get PL, how to get P prime, that we have just discussed in the previous equations. If we can have an expression for excess enthalpy, we can also convert it to excess heat capacity by its differentiation. So, that is what is mentioned in this comment. The DSC parameter Cpx, which is excess heat capacity, may be obtained from Hxt by numerical differentiation over small temperature intervals. So, what is done is, the excess heat capacity over a range of temperature is simulated from this equation, and the data is experimental data is subjected to a fit by this derived equations, and for whatever the value of KL, the fitting is excellent, that KL value is assumed to be the best estimated value of the binding constant. And that is what is written in the next comment. The value of binding constant is estimated where the simulated curve fits the experimental data points. Although the equations appear to be a little bit complex equations, but these are very easy to derive. The level of complexity increases when the binding mode changes from 1:1 to 1:2 or higher, or if there is instead of one thermal transition there are more thermal transitions. But nevertheless, appropriate modeling can be done, and for whatever the system is, it is possible to derive the value of binding constants associated with the protein ligand complexation by the use of differential scanning calorimetry. So, by now we have discussed the determination of the affinity constant or binding constants from a very low value to a very high value. And we also discussed that what range of the values of binding constants are suitable to be determined by isothermal titration calorimetry, and if the values of binding constants are very high to be determined accurately by ITC, one can go to differential scanning calorimetry and estimate the values of the binding constants associated with ultra tight binding processes. For further information on this topic, I refer you to the article published in Biochemistry in the year 1990, volume 29, page 6927 to 6940. Thank you very much.